Okay, so let's have a look at this real quick. They want us to answer a bunch of questions about kinematics, velocity, acceleration, height, etc. So they're giving us the function, this is the height function, right? Right here.
Yeah.
S of t equals 16t minus 0.2 t squared. And we got to answer some stuff. So they want us, first of all, they want to know, find the object's velocity and acceleration as functions of time. Okay, we can do that. So that's just differentiation, right? So v of t is what?
16 minus
T? Okay, agreed?
yeah.
Okay, and then a of t would be, okay, good, negative 0.4. Good. So there's the first parts. Second one, how long does it take the object to reach its highest point? Okay, so this is, it's probably, you would have an easier time with this if you were in the physics class. You don't need to be, but it would be a little easier. So we can talk more about this. Say it again.
What's the object's velocity at that t? Is that what the...
Oh, that's what that is right there.
Okay.
Right.
Sorry.
Okay, that's all that is v of t, right? And then acceleration is a of t. So, but to reach its highest point, now we have to be able to identify, and this is good practice, additional practice here in physics. But if we want to find how long it takes to get to its highest point, we have to figure out some kinematic quantity that's going to identify the highest point. What's something that we know? What's a value of either height, velocity, or acceleration that we would know when it's at its highest point? David?
Velocity will be 0.
Velocity can be 0. Good. So all we have to do then for this one right here is we're just going to set velocity equal to 0, right? So 0 equals 16 minus 0.4 t, and solve for t, right? That's our velocity function. We're setting velocity equal to 0. What would we do? We could add this term to the other side, I guess. 0.4 t equals 16. Divide by 0.4 and get 40.
Negative.
Well, but I just added it to this side.
Oh.
Right. So t equals 40?
Yeah.
Right? And I guess that's the answer they wanted. Then for part C, they want to know how high does it actually go. So where would I go to find out?
40.
Into the position or the height function, right? So now we know that if t equals 40, and I want to know how high it actually goes, I just substitute that in, right?
Wait, don't you plug it into the t?
I do. So what I'm calculating is s of 40 equals 16 times 40 minus 0.2 times the quantity 40, or times 40 squared. And that's going to give me something.
320.
320.
There's a d and e. And that's the answer to c.
So that would be the answer to C, yeah. Okay, now there's some other parts. They want to know, when does the object first reach half its maximum height? So how am I going to solve that one? Okay, good. So I know, well, no, that's not it. Now let's talk about y for just a second. So I can't just say it takes 40 seconds to get to its maximum height. Let me ask you this. Is it going to get the first half of that trip or the second half of that trip? Which one is going to occur faster? The first half, right? Because the velocity is always slowing down as it's decreasing as it rises. And so the average velocity for the first half of the trip is going to be much higher than it is during the second half where it's going to 0, right? So it's not just 20. I'm going to have to solve something to find it, but what's that something going to be? Oh, there we go. Okay, so would you agree? Half of its maximum height, we know that's going to be half of 320, right? Because the maximum height we just calculated is 320. So that's going to be 160, right? So all I have to do then is set the position function, the height function, equal to 160 and solve.
How do you know it's 160?
I know it's 160 because the answer to part C was how high does it go? And it was 320. So half of its maximum height would be half of that 320.
Yeah. You just said it equal to 160. Wait, so what equal to 160?
The position function, right? Because, now, let me make sure, I don't want you just to know how to do this problem. I want to make sure that makes sense to you why we would do that. The height function tells us the height of the projectile as a function of time, for any time, right?
Yeah.
So if I knew, would you agree, thinking in reverse, if I knew how long it took to get to half of its maximum height, I could just plug that value of t in and get half its maximum height, right? But we're kind of working backwards. We know the answer is 160. We need to find the time at which that happens, right? So then by setting 160 equal to this expression, 16t minus 0.2 t squared, I now get a quadratic equation in t that I could solve. And I'm asking the math gods then, essentially, for what times is the projectile at 160 meters?
So we choose when we put it in the aqueduct, you choose the biggest.
We're gonna, the smallest, because they wanna know, you're right, because on this one, they're gonna wanna know when does it first reach half its maximum height. So it's gonna reach it once on the way up, right? Then it's gonna stop at the maximum height and come back down and fall through 160 again, right? So if we were to solve that, we're gonna set up a quadratic equation. If I add everything to this side to get a positive coefficient of t squared, aren't I just gonna get 0.2 t squared minus 16t plus 160 equals 0?
Yeah.
Okay, and I'm gonna, I can use technology to solve that. I'm gonna get two real solutions. Both are gonna be positive, aren't they?
Yeah.
They should be. And I would know that if I didn't get two positive real solutions that I messed up, right? Because it has to be that way, doesn't it? We know physically what happens. It'd be pretty surprising if we shot a projectile up in the air and it never came back, unless it had greater than escape velocity. But this equation is not equipped to handle that kind of physics. This equation only handles normal physics near the surface of the earth. And I don't want to confuse you, but we would always expect, so just forget what I just said. We would always expect to get two positive answers, right? Because we know that what goes up must come down, and it's going to have to go through a certain height twice, once on the way up and once on the way down, if it gets to that height, right? What do you think might happen if I asked it, at what time will it be at 1,000,000 meters? I'm not gonna get back. What kind of solutions do you suppose I would get in that case? I would get some imaginary solutions, because there are none. There are no real solutions, positive or negative, right? Does that make sense? I mean, does it ever, so if this is the equation that predicts the height as a function of time, but we already know that the maximum height is 320, right? So if I asked it, well, when's it gonna get to a height of 1,000? The answer is never, because the highest it ever got was 320, right? And so we should expect the math gods to give us back an answer in the form of no real solutions, because there can't be any, right? And so if we didn't get that, we would, we'd know, okay, something's not right here, and we'd have to investigate, right? Okay? So then we just solve that. We get two answers, we take the first one. All right, the last.
Take the lower one.
We take the lower of the two, wouldn't we? Right. So what about part E? How long is the object aloft? Now there's a couple different ways we could go about this. What are some suggestions for ways that we could figure out how long this projectile is in the air? What do you think? So,
Set the first equation equal to 0, and then choose the length of the trial.
Okay, good. So the first okay, there's a couple ways we could do it. We could set the first equation equal to 0 and solve, and that's fine. That's one. Does that make sense? If I set the first equation, the height equation equal to 0, that's like asking the math gods, when is the height equal to 0, right? And that's a pretty easy one to solve, actually. if I set this equal to 0, I just get, what do I get? So 16t minus 0.2 t squared equals 0. Well, I can just factor out a t, can't I? Agreed? And then I'm just going to get t times 16 minus 0.2t equals 0. Well, what are my two solutions to that? Either t equals 0 or t equals what? 16 divided by 0.2, so 320? Is that right? No, 80. Whoops.
Same thing.
Okay. Right? Which one would we want?
80.
Okay, was there an easier way to do it, Riley?
Just double the 40.
Yeah.
That's what I was.
Yeah, good, because we already know it took how long to get to its highest point, right? 40 seconds. Now, what do we know about the symmetry of this? We know that the trip up has to be symmetrical to the trip down, doesn't it? Because the acceleration is constant. There's a bunch of ways you can think about that. We talked about the movie analogy. You could film the upward journey, and the downward journey would look identical to a reversed version of the upward journey, right? The other way you can think about it is, you can kind of just finesse your way through this. We know that the object is losing as much upward speed every second as it's going to gain in downward speed on the way down, right? So doesn't it make sense then that it's just going to transpose initial and final velocities, right? It's going to start with a big upward velocity, end at 0 on the upward journey. Start at 0, end with an equally big downward speed on the way down, right? So we know that it's got to be symmetrical in time. What a weird concept, but it's a very valuable concept. This is one of the things, I think, when you get to calculus, especially if you sync it with physics, you kind of start to look at some higher types of symmetry. We're used to thinking about symmetry. Remember back in geometry class when you talked about rotational symmetry and you talked about how many lines of symmetry are there for a polygon and things like that. We've always thought about symmetry as being something maybe physical, right? Something that's, or by physical I mean something that's graphical, right? Even when we talk about even an odd symmetry of a function back in Algebra 2, same thing, right? We're talking about, does it reflect over a line or does it rotate around a point, right? But there are other kinds of symmetry that are just as important, if not more. Symmetry in time. You can't see symmetry in time, but symmetry in time is hugely important in physics. Symmetry in time, it's, there's an important question in physics that seeks to ask, why is it that if a coffee cup or if a coffee cup gets knocked off a desk and it shatters when it hits the ground, why can't we reverse that situation? Why don't we see coffee cups spontaneously, shards of coffee cups, spring together onto the desk? Well, that's because that symmetry in time doesn't exist in nature because of entropy. Those are questions that we want to investigate, right? So symmetry in time is a big deal. Here you kind of get to your first glimpse of that, in a real situation.
What do you round D to?
Say it again.
What do you round, answer D to?
Answer
Like
D.
11.
Oh, okay. You don't need to, because of sig figs. Is that what you're thinking of for physics? Don't worry about it.
No, I mean,
Oh.
for on the test, it's probably
2 decimal places. Probably 2.
Oh, is that what
It'll tell you, yeah.
Yeah. Oh, yeah. It'll always tell you right here.
Oh, sorry.
Yeah. That's all right. Okay, so that was a good one to ask about. Any other? That one's done. Let's go back to back to here. Any others?
I'm gonna forget all this.
Did we go over 9?
Number 9. Yes.
Oh, never mind, that's an easy one. I'm trying to think of part. We've gone over all the part ones, haven't we?
I think we pretty much have now.
Wait, did we go through 6?
Let's do this one now.
Let's just look and see what this one is.
I remember thinking about the news about no.
Why is that not? Come on, pop up, buddy.
This time we're done. I didn't say that. Cindy said that.
Oh, like it was.
Oh, here we go. Okay, we did that one, didn't we?
Yeah. Oh, I skipped over it. I skipped over it.
You can do it.
Okay. Can you have a look, please, real quick? So this guy here, if we're supposed to calculate, the question was find the second derivative. Okay, the second derivative conceptually is just not a big deal, derivative of the first derivative, but the problem you run into here, of course, y prime equals what?
Four. Negative 4 cotangent. Cosecant cot x.
Cosecant, cotangent, okay, good. Exactly, okay, so then when you differentiate the derivative here, it becomes a product, doesn't it? Right. So that's what you gotta be careful about. So we're taking the derivative of this derivative, and this is a product. So when we take this derivative, we have to use the product rule, right?
Yes.
Okay? So I think we did secant, I think. So we did this one. This one's already on
Can you
video.
keep going?
Yeah. You want me to keep going with this?
Yeah.
Okay. All right. So here's my recommendation with this. I would say you leave the -4 out front and just differentiate the product. So I would do this. I would say there's -4 out front, and now we're going to use the product rule, right? So the derivative of cosecant times cotangent is just going to be first times the derivative of the second. What's the derivative of cotangent? Good. Negative cosecant squared plus the second times the derivative of the first, which we already did. Cosecant x, negative cosecant x, cotangent x, right? And so now all we'd have to do is just distribute the -4 back through, and we'd be done, right? We'd end up with -4 times negative, it's going to give me positive, for cosecant cubed x, cosecant times cosecant squared, right? Negative times negative is positive for cosecant x cotangent squared x, right? And you could even leave the 4 out front if you want to, I suppose. So that's really it. I mean, we don't need to go, at this point, we don't need to go any further with that. As I've said a couple times, when we start to use these derivatives to do interesting things next chapter, like find minima and maxima and inflection points and things like that, then we're going to have to maybe simplify this in a targeted way. We have to factor it, but we don't have to do that now. Okay?
Wait, 1 second.
Sure.
Sorry. Okay.
Okay? Is there? I don't know. Is there anything else? We'll look, I guess. I don't know if there's going to be anything else or not.
Did we do 6?
Sure.
Like, did we? We might have.
Well, let me look. I can't remember. I don't think we did. Should we do that one?
No, we did do that one.
We did do this one?
Yeah, that was the quotient.
Yeah, but we should do it.
Sure. Okay. Okay. So this is kind of a tough one in a way because it's a chain rule problem that also involves a quotient rule, right? So if we're going to differentiate this then at the outermost level, what have we got?
2.
Yeah, we got hand squared, right? So 2,
Yeah.
2 hand to the 1, right? And hand is negative sine x 1 minus cosine x. Okay, so this is unfortunate, right? Because now the derivative of hand is a quotient rule issue, right?
Yep.
Yes.
Okay, so Hunter, how are we gonna do this quotient rule with it?
Just break it apart. So you're gonna do your tidy low or like. It matters. It does matter.
Well, no, it does matter.
Yes, it does.
Okay, so we got bottom times derivative of the top. What's the derivative of the top?
Negative cosine x.
Good. Times negative cosine x minus top times derivative of the bottom. What's derivative of the bottom? Sine x. Everybody see that?
Yeah.
Derivative of 1 is 0. Derivative of cosine is negative sine times negative 1. So positive sine.
Wait. I always get so confused.
Whoa.
So cosine.
So the derivative of the bottom, we have the derivative of 1 is 0. We can discard that. Minus the derivative of cosine is negative sine, right?
Yes.
But I have a negative 1 out front, so that makes it positive. Okay, all divided by
1 minus cosine x.
good, 1 minus cosine x quantity squared. And so really all we've got to do then is just simplify a couple steps. We're going to simplify all of that stuff, and then we're just going to multiply straight across, right? So if we simplify all this, let's see if we can do this quickly. So we're going to get 1 plus, I'm not 1, we're going to get negative cosine x, sorry. If I distribute the negative cosine x, okay, right, but we're going to get a negative cosine x plus cosine squared x minus negative sine squared, so that's plus sine squared x, right? Okay, but what is cosine squared x plus sine squared x?
1.
That's 1,
Okay,
yeah.
I thought there were no identities in that.
Well, maybe I lied a little bit.
Oh, yeah.
That's, okay, but that's one that, you know, you gotta know that one. What's that? I did, I gave you a paper to use on it though, so that's okay. That's fair game. Times.
Oh, he was floating. Yeah. You just did the opposite.
So we have that, agreed?
Yeah.
Okay, because, and that was a little sneaky, but because this, whoops, because remember, that part's equal to 1.
Wait, isn't it not squared on the bottom anymore?
Say it again?
Isn't the little pink two on the bottom not supposed to be there? It is.
That?
No. The pink and the pink.
Oh, yeah, because you already have it written.
Okay. No, you're right, because,
Why is it squared?
because I haven't done anything to it yet.
You see you combined,
You're right.
the,
I haven't multiplied across yet though.
you combine the blue.
Okay, I got you.
Okay, good. But what's another way of saying this? This is the same thing as the quantity 1 minus cosine x, isn't it?
Yeah.
Now, that's a factor. This is because it's being multiplied only by other factors on the top, and this is a factor on the bottom. Now, I can cancel like factors. So that and that cancel, right? And so I end up with negative 2 sine x. How did I get the pink? The pink, okay, let me backtrack a little bit. Everybody focus please up here. So how did I get the pink? Well, this part is just directly brought down to there, right?
Yeah.
The denominator of this big ugly fraction is right there. All I did was simplify the numerator. This just becomes negative cosine x plus 1, which is really the same thing as 1 minus cosine x, right?
Okay.
And so then I've got common factors, top and bottom, that can be canceled. And so I just end up with a 2 times negative sine x, which is negative 2 sine x, over the quantity 1 minus cosine x squared.
That's it?
That's it.
It seems a lot close to the original.
It is. It's very close. Yeah, it's kind of a weird one, isn't it? I mean, it looks almost identical. Mm-hmm. Yep. Okay. Good? Leave it? Okay, I'll leave it.
54.
2 minutes.
2 minutes? Okay, I'll quit there then.